A new word that's coming about within the markets and within literature is calling lithium, cobalt, nickel energy metals because they enable the storage of energy. And yeah, so if we can go to the next slide, I want to give my first key points. So the first thing that I want to say is that just like what we've seen with the magnitudinal demand that we're going to be seeing over the next 10 years, these energy metals will enable the industrialization of EVs. Really scaling and bringing more EVs to market will require these metals and the materials that they form. Next, if you look at the current EV battery packs, oh, can we go back? If we look at the current EV battery pack landscape, varies greatly in terms of the energy densities of the packs in the market, the cell chemistry, as well as the amount of energy metals used. And that's really a function of both those two other factors, the energy density and the cell chemistry. And while there's such an intense focus on these energy metals, when we look at actually improving cell performance, EV performance in the near term, it's really going to come from quiet innovation. So less headline-grabbing movements in the technology. And so I'm hoping to talk a little bit about that before wrapping up about how we're going to be able to capitalize on these innovations during the use phase of the vehicle, but also when the vehicles reach end of life. And I want to talk a little bit about some of the issues and questions that my thesis is addressing regarding how we make desirable outputs that the evolving material markets are going to want and demand. So next slide. So now looking more at how we connect these metals to the technology, we have 4 different electric vehicle models, 4 different cell suppliers, 3 different types of cells, and then ultimately we get to the cathode chemistry. And so it appears that there's really just two types of cathode, but I like to call them more 2 families of cathode, because the ultimate energy metal requirements really depend on the ratios of each of those metals, the ratio of nickel to cobalt to manganese. And so when we look at the far 2 left columns, the amount of cobalt and the amount of lithium required, both in elemental forms, it really depends on those ratios. And so on the left-hand side, so on the lower bound for cobalt, we have the NCM 622 chemistry, so 6 parts nickel, 2 parts cobalt, 2 parts manganese. On the right-hand side, we have NCM 111, which is equal parts nickel, cobalt, manganese. And so within the cobalt realm, as you go between those two members of the family, you see about a 50% reduction as you go towards 622. But if we look more on the lithium side, there's really not as much variation, and Alex captured this a bit earlier. We only see about a 10% change, so you're still going to need the same amount of lithium to support the chemistry, but ultimately the absolute amount that you're going to need is going to depend on your energy density and your pack size. So what we're seeing now, and you see sort of the lower pack sizes, those are really the first generation of the EVs. You also have the Teslas with higher pack sizes, and then you see General Motors kind of in the middle. And what we're seeing with newer models coming out is a sort of convergence around 60 kilowatt hours or 50 kilowatt hours, which provides that range, around 200 to 300 miles. So you're quelling the range anxiety that I think we've talked about in panels yesterday, maybe earlier today, but you're also providing, a product that people can use for daily life. So, certainly this is what we're seeing now. But what if we try to industrialize EVs? And so our next slide looks at how much cobalt we would need. So Elsa alluded to cobalt as a tight market. It's a much smaller market in magnitude to other base metals like copper. So the cobalt market's about 110,000 tons annual production. Copper, you're looking at 20 million. So very much looking at this smaller market, when we try to industrialize this pack size that we see converging in the market, we look at the cobalt requirement and looking at the NCM family lower and upper bounds. If we're trying to make 500,000 EVs, that's going to require between 5,600 and 11,000 tons, metric tons of cobalt, which in today's market at this supply, it's about 5 to 10% of the market, which is pretty significant. Now, some of the work at the Energy Institute, we've looked at what would be the raw material requirements to support future adoption of EVs. And so splicing the EV future production between BEVs, so large packs, versus PHEVs, or plug-in hybrid electric vehicles, smaller packs. If we just look at the BEVs, we're looking in 2020 about 3.5 million BEVs that we're projecting to be seen globally. So if best case scenario, if the market can all move to NCM 622, we're going to be still looking at about 35% of the current cobalt market going to the BEV segment. And that's not even PHEV. So it's going to be very important that we see new primary resources coming online, but also we start thinking about what we do at end of life so that longer term we can recover these important natural resources. So now taking a step back from energy metals, so going on to the next slide, we look at what are the OEMs looking to do about cobalt. So we're seeing this huge potential concentration of OEM use of cobalt. What are they trying to do? Well, there's the cost function. So cobalt's the most priciest or the most expensive energy metal component in the battery. But there's also a performance motivation to reduce the cobalt content. And so as we move, and if you look at the lower right hand side of the triangle, we see as we increase the nickel content, we increase the capacity of the cathode material, which is the limiting electrode for energy density. And so by decreasing the cobalt but increasing the nickel, we create the potential for a more energy dense battery. At the same time, we need a certain amount of cobalt to provide stability. And so that's more going into the safety segment of the performance. And so right now, what we're seeing with OEMs is that there is this range between NCM 111 and NCM 622, where it's still safe, but certainly the glide path is to go towards even higher nickel content batteries. And so that's going to require innovation, not only on the cathode side, but looking at how the other components of the cell are going to accept that innovation. And so if we move going forward to the next slide, we see what would happen if we continue to increase nickel on the cost side. When we see that nickel content's increasing, we look at what the cost of production would be. And while you do see a lower cost of cobalt because you're using less of it, if you look at the bottom technology band, as we move to higher nickel content, we use a different type of lithium chemical, which according to pricing agencies and looking in the market, this type of chemical, lithium hydroxide, fetches a premium over the current chemical that's used, lithium carbonate. So there is that processing cost or price concern, but luckily, as was mentioned earlier, the amount of the lithium resources that are coming online, the rock lithium resources, they're building additional refining capacity to produce hydroxide. So hopefully long term we'll see more hydroxide coming on, but still it's just optimizing as we go on this technology glide path for cost. So taking a step back now from the cathode market, I think that in the next slide we see that there's a broader amount of different components in the battery cell. So the cathode, yes, contains the energy metals, accounts for roughly a third of the battery cell, but there's still 2/3 of the cell that are open and fair game for innovation. And so looking deeper at the cell and thinking about the cell as a manufactured ecosystem, on the next slide we can see a schematic of a typical pouch cell. Standard design, tabs on the same side, likely a stacked electrode manufacturing process. And those green arrows are the movement of lithium ions. And then those arrows on top of those sheets, so the black and white arrows, that's the movement of current going from anode to cathode. And so thinking about this as a manufactured ecosystem, yes, we can make advances in the cathode, and it is the limiting electrode, but there's so much other things that we can do. And we can look at different types of liquid electrolytes. Could we use different additives to boost current electrolyte performance? Or should we scrap liquid electrolytes altogether and go to some type of solid electrolyte that allows for greater ionic conductivity? These are kind of questions that are being thought about right now, but ultimately it's about manufacturing the cells and balancing that material cost, manufacturing cost, and being able to scale it and industrialize it. So finally, though, we can make all these innovations and we can bring these products to market, but we always have to think about what we're going to do with the products at end of life. And so on the next slide, we look at EV battery recycling. And yes, with the current projections for EV adoption and the EVs that are going to be placed on the market now won't necessarily be able to contribute as much on a percentage basis for the requirements down the line. We still need to think about building those sustainable systems for how we recover materials. And at the first question that I like to think about generally, and we've talked about the timing a bit, but just when are these battery packs going to come back? Are they going to be 8 to 10 years, like normal personal use vehicles? Or, as was discussed yesterday with new mobility services, are we going to see changes with capacity or with utilization? That means that we're going to cycle these battery packs quicker or faster, and we're going to reach end of life maybe in half the time, maybe in 5 to 7 years. So really, that's going to accelerate our need potentially for recycling. Next, are we going to have the workforce and the labor capabilities to perform diagnostics on packs that come back? And will they come back to dealers? Will they come back to service centers? It's going to be important for us to have those people trained and technicians ready to meet this new demand. And then finally, because the cell chemistries are evolving so much, what is going to be the prevailing cell chemistry 8 to 10 years from now? And will the constituents in the battery make sense to recycle? And in what form should we try to recycle them in? And that gets at this ultimate material recovery process, because there's a lot of discussion about ways to make it economical, ways to produce something that's more flexible, but ultimately we just need to make something that's desirable for the materials market. Because ultimately we want to reintroduce these into the battery supply chain, or perhaps just be able to fetch enough value, perhaps in other industries. And so to end, I'd just like to encapsulate those thoughts in a diagram on the last slide, so moving here, about how we could close the loop. And again, moving left to right, we look at some of those more social, economic consequences. So looking at, how do we train people? How do we build the systems for collection and diagnostics? And then moving more on the design and engineering side, how do we design these battery packs for disassembly? So, would we be able to take a pack, take it to a module level, ultimately get to a cell level, and then will we have the businesses or services available to reduce them in size, separate the plastic, separate the casings, and then even after that, we'll have to go after those energy metal containing those active materials that contain energy metals, and even then, as we've discussed, there's certain level of backwards integration where we look at either pure metals. We look at the metal salts, so the cobalt sulfates, the nickel sulfates, even lithium carbonate hydroxide, and then ultimately that one component that's then added into the cells, the active materials. So there's a lot of discussion now about the flexibility of these recycling processes. A lot of folks are saying yes, active material, definitely the way to go. It fetches a very high price in the market, but that's the market today. What is the market going to be in 8 to 10 years or 5 to 7 years? We have to think about designing the processes to produce desirable outputs. And so it's going to take a certain level of technology, process scaling. It's going to take certain amount of policy as well around how we govern the use of these resources, govern the use of EV technology, and then perhaps also some entrepreneurial grit around how we are able to develop new types of businesses. And so I'd like to leave that with you guys to discuss in the panel, but very much excited about being in this space. You know, it's very much the pioneering of resource efficiency. So thank you very much, and look forward to the panel.